Okay guys, welcome to lesson 3 of the particles topic, and today is the big one, latent heat and specific heat capacity. My advice is watch this from top to bottom first, then go back, watch it in each section and make notes as you go. There's going to be 2 equations, some new terms along the way, so I'll keep a keywords list on the right hand side as well. So off we go. One of the first practicals you ever do at Mullion School is measuring temperature. And it's a nice simple one. Give you some crushed up ice, give you a beaker, a thermometer, gauze, and a heat Bunsen burner. God, you can tell I've been away for a month. I've forgotten the words. And I usually say about every 30 seconds, measure the temperature. And I always like to ask the kids, what do you think the graph's going to look like? So if we take this graph here, and across the edge here, we've got temperature. And along the edge here, we keep the time. And I usually get them to do it in seconds. And you ask them, what does the graph look like? Given that it, hopefully starts about -10. And pretty much every kid will write that. It gets hotter. It might go slow, might go fast if the Bunsen turns up. But they always just draw a straight line. However, if you do it in real life, what you get is not that line. So let me draw it for you. It goes up. But then a strange thing happens. It goes across, and I'm going to draw that in a different colour. I'm going to draw that in blue. I'm going to go across. So there's a period of time of heating where the temperature doesn't go up. Then it goes up again, heats the water up, but then the same thing happens again. Water cannot go above 100 because it's now boiling. And then finally it goes across and it goes up. Now, it's really hard to see when you've got a bunch of year 7s. They're taking every 30 seconds. It's kind of blinking, you miss it, and it hops across. So you very rarely get this. Ideally, you'd want to be doing a result every second. So for that, you'd want to use a computer and a data logger. Here we have a solid. Here we have melting. I'm going to draw this graph twice because I'm going to annotate it differently next time. We've moved then to a liquid. We've then gone to boiling. And then finally, we've gone into the gas state. So that's our first thing to note, is that it goes in that shape. If we were to look at cooling, exactly the same thing would happen. We'd get the inverse of that. So let's draw a cooling one. Same kind of shape again. The axis, time there, and temperature there. And if we would take a gas, so water again, steam, 0C, 100, 0, there we go. And let's go to -10 again. So if we were to freeze it, we'd get exactly the inverse shape. So we'd go from a gas, we'd cool, go along. We'd then move across to condensing, to a liquid, across. We'd then go back to the liquid state, and the liquid would cool and cool and cool. So we got to the freezing state, and we would go across like that. And final thing, we'd then go to the solid, and the solid would get colder and colder. So again, we can label those up. We can go from a gas to a liquid to a solid. And from last lesson, we looked at the names of these. So from a gas to a liquid, we'll say condensation. Or condensing. Condensing. And for here, we're going freezing. Now, let's take a bright purple. Let's make it a little bit chunkier. So let's have a look what's going on in the first one again. All the time that time is going past, we are adding energy. You want your ice to melt to a liquid, you're going to have to heat it up. You're going to have to put energy in. However, when we look at it this way, then we've got energy being removed. If you take away the heat energy from a liquid, it turns into a solid. So the first thing we can say that's kind of new to this is we're adding or removing energy. Next. This is where it gets tricky. If we were to look at a state of matter, so let's take a solid, for example, we know that it has energy, and there are two types of energy that it has. So let's draw our solid in there. The first one's quite easy. We said that they're vibrating. So if we do this, they're vibrating against each other. And vibrating energy is movement. And can you recall what type of energy is movement energy from topic 1? I can hear all your voices shout in unison. Kinetic energy. Kinetic energy is the vibrations of the particles. Hit the button. Particles. So that's easy. We can measure the average kinetic energy of those, and that's the energy inside. But there's another one, and this one's more subtle. And for that, I have to zip over to GPE. And if you remember in GPE, in gravitational potential energy, we said that GPE was an object off the ground, and the higher it was, the more gravitational potential energy was in it. So this had more, and this had less. Because the distance from it to the ground, as it got greater, if you remember the equation is GPE is equal to mass times gravity times height. The greater the height, the further away it was from the Earth, then the more energy it had. Well, now look at these particles. These particles are very close to each other. So it's not gravitational energy they have. We call it purely potential energy. So type 1 is kinetic. Type 2 is potential energy. And we'll say potential energy is the energy stored by virtue of the interparticle distance. Okay, so don't mix it up with GPE. That is just a type of potential energy that's showing you that the distance increases the amount of energy. And in this case, it's caused by gravity. In the case of this one, it's a chemical one. What happened there? A chemical potential. But we literally just, in physics, we just put potential energy. So what we can say now is the solid has, and this is a new keyword, internal energy. I'm going to highlight it in bright purple. Is totally a keyword for today. Has internal energy. We can write it out like an equation. We can say internal is equal to kinetic energy add potential energy. So the total amount of energy inside that solid is its kinetic add its potential energy. So now let's have a look at a liquid and see what's going on. So if we go from a solid now to a liquid, you remember we've added heat energy to this, so we're putting energy in. Let's have a look. We'll draw the particles again this time. I'm spreading them out. I'm drawing more vibrations on them. So this time we can say that they have more vibrations. That was from lesson 2. But because they have more vibrations, that means they have more kinetic energy. And look at the gap in between them. They also have more potential energy. More potential. And where did that energy come from? Well, it came from the heat that you were putting in from the Bunsen burner. So that heat is causing more internal energy. More internal energy. So a liquid contains more internal energy than a solid. And so you can see where I'm hopefully going with this one. We'll do it small enough to fit on this page. If we go for a gas now, it should be really obvious now why a gas has even more internal energy. Because it has even more kinetic energy. The particles are moving extremely fast. And it has way more potential energy because the particles are extremely far apart from each other. So even has greater kinetic energy and potential energy. So that is this keyword internal energy. What it means, you will fairly reliably get asked this equation here. It's not really an equation, it's more a thought pattern. But be totally prepared to learn that, recall that, and then you refer to this repeatedly in your answers when you're describing things. So back to my graph now, and where these two big equations come in. Let me take a copy of, I'm just going to focus on the heating one for now. So I'm going to make a copy of this thing and I'm going to paste it down here. So I'll teach you it first and then I'll tell you the name of it. I'm going to get rid of these parts here. I'll leave the solid, but I'll get rid of what's going on. I'll get rid of that. Okay, so let's look at this part here, solid. Here we've got a solid that's at -10. Then it becomes -9, -8, -5, -4, 3, 2, and then it becomes 0. All the time it's heating up, but all the time it's still a solid. So it's still solid, but heating up. So in terms of its energy, let's think about it. When it's at -10, the particles are in a solid arrangement still. They have vibrations. So its internal energy is equal to its kinetic plus its potential. Right? But when it's at, so if that was -10, when it's now heated up, we've added more heat to it, it's now at, let's say, -1 degree. Let's put degrees Celsius. It's still a solid, it's still ice. However, one of the energy stores has increased and the other one hasn't. So, can you figure out which energy store increased? Press pause or just, I'll wait for a second. Okay, hopefully you're all saying that the kinetic energy store increases. However, the potential energy store, it's still the same drawing. If I drew those in, it's still the same solid. It remains the same. It hasn't got further apart. So when we're looking at these red lines, these heating parts, we're actually only talking about the kinetic energy increasing. So we can say, when heating, only the kinetic energy store increases. So for example, if we took water at 1 degree, so +1 degree, and we took water at +99 degrees Celsius like that, the only difference between them is its kinetic energy. So Ke increase. Same for the gas, the Ke increase. And same for the solid, Ke increase. Now we can calculate that, and this is the first equation. The equation is called the specific heat capacity. Told you it was a biggie. And here's the equation. The change, delta, I think we've covered delta, but delta, physicists use it, sometimes mathematicians. It just means change. Okay, so change in energy is equal to how much stuff there is in kilograms times this special number called the specific heat capacity. And I'll talk more about that in a minute. It's easier than you think. And that is measured in, now let me get this right, how many joules per kilogram degrees Celsius. Don't freak out, I'll sort that out in a minute. Times the change, delta, in temperature. I'll just put I'll put the full word. Temperature. So let's look at it algebraically. You'll see it written as delta E is equal to mc delta theta. Now, you're looking at that and hopefully you're going, we've used that in maths before. And yeah, theta is used to denote both the angle or the temperature of something. So I'm going to colour code these. So delta E is easy, delta E. Mass is measured in kilograms and there's mass. They used C, don't ask me why, for specific heat capacity. They didn't use initials. And delta theta is the change in temperature, and there it is there. So that's the matched up. It does go into a triangle, even though it doesn't look like it should. And the triangle, to find the missing parts, will be this. Let's get off that a minute. Let go. There we go. So it goes delta E, and then we have two bits, and it's mc delta theta. So we can rearrange it, and I'll leave you to figure that one out. It's easy enough. But what does it mean in real life? Well, say you had tap water. Comes out of the tap. So you got tap water, and you're filling up your kettle. And the question is, how much energy do you need to put into your kettle to heat that mass of water, to boil it, to make a cup of tea? So we can work it out. We can look at what's the starting temperature. So at the start, tap water is 20 degrees Celsius, pretty reliably. We want the end temperature to be 100 degrees Celsius. So straight away we can say delta theta, the change in temperature, is 80 degrees Celsius. Next, we need to know the mass of the water. So let's say we're going to chuck in, keep it really simple, 1 kilogram of water. And the final thing is C, the specific heat capacity. Now, that number is a textbook number that a scientist has measured and is put in a journal, and it's constant for every liquid. And what they do is they take a kilogram of a liquid and they ask themselves this one question. How many joules of energy do I have to put in to raise the temperature of this 1 kilogram of material by 1 degree Celsius? And the answer for water is, I think, 4,600 joules to raise 1 kilogram by 1 degree Celsius. So if I take a kilogram of water and I want to make it go up from, 20 degrees to 21 degrees, I've got to put 4,600 joules in. So we put that number in. You always get given it. You're never expected to memorize these numbers. So it's joules per kilogram degrees Celsius. And then we just run the numbers. So we get 1 times 4,600 times 80. And we should get... Let's give it a go. Is that going to bring up Siri? Brilliant. When you want Siri, it's never there. When you don't need it, it pops up. And now, multiply them together and you will get an answer. Let's give it a go. 4,600 times 80. Calculator down the side. 4,600 times 80 is equal to 0, because there was a 0 in there. 4,600 times 80 is equal to 368 kilojoules. So let's pop that in. Equals 368 kilojoules. So that's how much electricity, at a minimum, you're going to need to put in to heat that water up. And you can see straight away, you might have a dad or a mum who's really fastidious on this, that when you fill the kettle up, do not fill it all the way to the top if you only want 1 or 2 cups of tea. Because if you put 2 kilograms in there by filling it up, you're now going to need double the energy to boil it, and that's going to cost more money on your electric bill. In reality, though, that will probably be 450 kilojoules. Can you think why it's higher than that calculation? Have a thought for a second. Okay, hopefully you're all realising that it's not perfect. The heat is going to radiate out. And so to heat that up, you want to insulate it as best you can. And kettles actually aren't that really good at being insulated, particularly if you have an old metal one. They do have plastic, but they're not like a thermos flask. So you end up putting more energy in than you actually need, just to cope with all the heat losses. Now, I have seen this come up a few times in exam questions. They get you to calculate it, like we have here, but then they'll say, yeah, but it required more energy. Why? And this is the reason. You get energy loss. So now we can look back at our chart here, and we see that the red ones, this one, and this one, all require the specific heat capacity equation. They will all tell you how much energy, if this is time and time is energy, you know, if you've got your Bunsen burner on, every second that goes by, you are adding more energy. This will tell you how to get from here, 20 degrees Celsius, going across to get to here. And this will tell you delta E. It'll tell you the amount of energy you need to get from one temperature to another. And that's a specific heat capacity. I'll put it in red to match the lines on there. So that's that one. Told you it was a bit tricky. Next one. If I take a grab of my graph again, so I'm going to take this one. We're in the home stretch now, and this equation's easier. So we'll go copy, and we'll paste this one down here. Paste. And we tidy it up again. Now I'm going to go for the blue bits, where it's going from one state of matter to another. So I'm going to take out the boiling and the melting phrase. So the bit I'm interested in now is here. As I've gone from a solid to a liquid, well, if we were to draw it again, we've now gone from there to there to there to there, solid, and we're now increasing the gap between them. However, look at the temperature. 0 degrees Celsius, 0 degrees Celsius. So hopefully you're starting to think, So have a few seconds. What am I going to write next about this solid and this liquid? What's going to change? What's going to stay the same? Okay, hopefully then, let's give it a go. I'm going to take these. I'm going to drag them over here. I've gone from a solid to a liquid. Look at them. Their kinetic energy has stayed the same. And they've stayed the same because the temperature is the same, 0 degrees. It's only when you go up in temperature, 1, 2, 3, 4, do you increase the kinetic. So here we can say the kinetic has stayed the same. However, what has increased is the potential energy. The bonds have been broken. So potential energy increases. And that's because the bonds have been broken. Bonds have been broken. And now it's changed state. So all that heat energy we've been putting in, as we've put it in, it's not going into the kinetic energy store. The heat is going into the potential energy store. And you can think of this like Lego. Imagine you've got a load of solid Lego bricks all clicked together. What you're doing now is you're spending your energy disconnecting the Lego bricks. You're breaking the bonds, pulling them apart. So in terms of an equation, it's loads easier. This is called the latent heat equation. It's got less bits in it. The equation is change in energy is equal to m, the mass, times the latent heat. Delta E is measured in joules, mass is in kilograms, and latent heat is how many joules per kilogram. Loads easier. Algebraically, it's written as delta E is equal to mL. Easier to remember. I'm pretty sure you do get this in the equation sheet as well. So let's colour code everything, make sure we're sure on what matches what. So we've got mass matching M and latent heat matching L. There it is. Goes nicely in a little triangle, as you can imagine. Oh, that worked out better than I expected. Delta E, the change in energy, is equal to mL. And let's have a look at what it actually means. So, latent heat, how many joules per kilogram? So, scientists again found the textbook answer. You take a kilogram of a material, doesn't matter what it is, you take 1 kilogram. So, say we took it of ice and we asked ourselves how much energy, how many joules to convert 1 kilogram of solid ice into 1 kilogram of solid liquid. And it's a figure, and they got it. Now I'm going to look this one up because I can't remember it. So let's have a look. So we want the latent heat of ice. Ice to water. It's a bigger number. So they've got that there in... this is a problem. The Americans insist on using Fahrenheit. So if you come across an American website, it usually gives you it in the wrong way. There's specific heat. Hopefully this is latent heat. There we go. Here you go. It's pretty big. 3.34 times 10 to the 5. So 3. How can I forget that so quickly? 3, 10 to the 5. 3, 4 times 10 to the 5 joules per kilogram. Now you may have seen it, by the way, written here as joules kilograms to the -1. Hopefully you've all learnt that 10 to the power of -1 is the same as 1 over 10. So if you have something where you are doing a division, if you do joules kilograms to the -1, it's the same as doing a divided by. And that's where that comes from. So when you do A-level, you'll write everything all in a straight line, and you'll just use to the power of -1 to denote the reciprocal, the inverse, the over. So that's the latent heat. Now there are two values quoted. We've got here solid to liquid. So we call that the latent, it's a bigger word than it really needs to be, latent heat of, my brain's gone dead, latent heat of fusion, that's it. What it's telling you, it's the amount of energy within the bonds that fused it. So latent heat of fusion, big time keyword there. The other one is called the latent heat of vaporization. because you've vaporized it going from a liquid to a gas. Now, there's separate numbers for each one, and you will always be given them. And I'm pretty sure I spelled vaporization wrong as well. No, I did not. Makes a change. I usually chuck in a cheeky U in there somewhere. So we can have a go. So let's imagine we had, e.g., we had 0.5 kilogram. So we've got the kettle, and we wanted to boil all the water away. We wanted to take 0.5 kilogram of a liquid, and we want to evaporate it all away, boil it all away into gas. The question is, how much energy is it going to take? So we need to look up the latent heat of vaporization. We look up that term. So if we go to this site, I think they've got it here. Don't crash. Coming up. That sound in the background you might hear is my 7-year-old. I promised to go and play frisbee with him, and it's getting late, so he's panicking. 22.64 10 to the 5. 22.64. 22.64 times 10 to the 5 joules, kilograms, minus 1. All right, and we've got 0.5 kilogram. So all we have to do is use the equation. Change in energy is equal to mass times L vaporization. Put it in. 0.5 times 22.64 times 10 to the 5. And the answer is going to be, here we go. Come on, you can do this. 11.32 times 10 to the 5 joules. So going back to here, the blue ones are latent heat equations as opposed to specific heat. Told you it was a big one. Hopefully you've got to the end. You haven't fallen into a coma. It's quite heavy duty stuff, and this is why I needed you to do the first lesson, the second lesson on states of matter well. My advice is go back over it, pause it, make notes. The page numbers again were pages 39 and 40. There'll be questions below. Any questions in the comments or email me directly. I will be doing a revision lesson on this as well on Zoom, so hopefully you'll join me then. And hopefully then you'll go on to the next lesson, gas pressure, and that'll be the end of that topic.